Well, thank you so much for the invitation to talk at this conference. It's actually my first time at KITP, which is awesome. I've always heard great stories, so it is really exciting to be here. So today I'm going to be talking about, sort of broadly speaking, how we're thinking about simulating strongly interacting physics on modern-day quantum devices. So my focus is really thinking about the quantum devices that we have right now, not what we're going to have in 20, 30, 40 years when we have, large-scale fault tolerant, if we're lucky. So the motivation, both for this work and really sort of for my physics, is sort of twofold. The first is if we really want to understand the standard model fully and completely, so being able to compare experiment to theoretical predictions, we really need to be studying the properties of strongly coupled theories from first principle without approximation. That's really how we can get the bounds that we need. And secondly, thinking more of a beyond the standard model physics, non-perturbative quantum field theories, so strongly coupled field theories, have this really rich and beautiful phenomena, and it's a really great place to look for new answers to the big questions. It just tends to be a little bit hard to probe. Now, we have a great example where we see sort of both of these motivations, and this is Quantum Chromodynamics, QCD, as everyone here knows. So QCD, it provides a precise and quantitative description of the strong nuclear force over a broad range of energies, which is amazing. It also gives rise to a complex array of emergent phenomena. Particularly, not all this phenomena can be identified from the underlying degrees of freedom, so just from looking at the quarks and gluons. So for example, we have the proposed QCD phase diagram, and notice it's proposed, it hasn't been sort of verified fully, because again, hard to calculate. And you can see that there's a lot of different behaviors that emerge out of this relatively simple theory. And then lastly, as I mentioned before, if we really want to compare theoretical predictions of the standard model to experimental results to make sure that we're correctly encapsulating fundamental physics, we really need to be doing ab initio calculations. And so all of this sort of brought together, this idea that we should be doing classical simulations of gauge theories using Lagrangian formulations. And this goes back about, now at this point, 40, 50 years to Lattice QCD, where we have it's a highly advanced field that utilizes high-performance computing to probe the non-perturbative properties of QCD from first principles. So this is sort of the bedrock of really doing first principle studies of QCD. Now, since not everyone here is a numerical lattice expert, I want to give a quick overview of Lattice QCD, very quick. So spacetime is discretized onto a hypercubic grid, so both space and time are discretized. The fundamental degrees of freedom are mapped onto this grid, so the fermions tend to be on the sites, the gauge bosons, the gluons are defined on the links connecting the sites, they're the parallel transporters. Now in order to actually put this onto a classical device, we use Monte Carlo importance sampling, which is used to calculate expectation values of observables. And the really, really cool thing about this is, lattice QCD methods were proposed, 50 years ago, maybe even more at this point. But now really due to impressive algorithmic developments, not so much that computers got bigger, it's that the algorithms got better. We now have real world calculations. So calculations at physical pion masses. And I will say the reason why I love lattice methods is it's a fully systematic approach to ab initio computations in the non-perturbative regime. Now, you might say, okay, well, if you love classical lattice so much, why are you thinking about quantum devices? And the answer is, well, classical lattice methods don't give us everything that we want. And in particular, one problem where they really struggle is in places that have sign problems. So for example, if you think about lattice simulations again, we're doing numerical estimations of lattice regulated quantum path integrals, and that really requires the existence of a positive probability measure. So if I have my path integral, highlighted in blue is a thing that must be real and positive to do Monte Carlo importance sampling. And unfortunately, in a lot of places that we are interested in looking at, we have sign problems, which prohibits a first principle study of these theories. So 3 places where we see sign problems is real-time dynamics, so things like early universe space transition, scattering. This is because they require Minkowski space simulations, and classical lattice is always done in Euclidean. We want to think about finite density nuclear matter, so neutron stars, QCD phase diagram. That fermion determinant becomes complex. And lastly, during the first talk of this conference, we talked about chiral gauge theories, or David talked about chiral gauge theories. We need to have a lattice-regulated chiral gauge theory to have a fully defined standard model. There we have a complex fermion determinant, so we can't really simulate them using classical devices. So now the question that I'm really trying to get at is this kind of physics, places where there are sign problems using classical methods, is this physics more accessible on quantum computers? So that's going to be sort of the focus of the majority of my talk. Okay, so in contrast to sort of classical lattice QCD of classical lattice, we can talk about digital quantum simulation and quantum lattice. So for me, quantum lattice is essentially a very young field which utilizes NISQ era, so near noisy intermediate scale quantum devices, it's a very young field that tries to carry out exploratory studies on lower dimensional toy models using this NISQ hardware and also quantum simulators. So the sizes that we're able to access right now can still be put onto quantum simulators, but that will shortly stop being true. And the general approach that a quantum lattice simulation uses, this is not always true, but this is how I think about it, is you do a simulation in 3 steps. So you start off on the left, moving to the right. So you start off with some initial state preparation. You initialize your quantum computer, maybe into the ground state, maybe into some excited state. Then you evolve via multiple applications of the time translation operator. Here I'm really thinking about Trotter time evolution. There are other options. And then lastly, you carry out a measurement. Now, this is a quantum process, hence a quantum computer. So in order to build up the expectation value, you have to run this circuit multiple times. So that's kind of the schematic of how these simulations look. Now, the overarching research goal for a lot of us in this field right now is how do we take the theory that we're interested in, so namely QCD with light fermions, how do we rewrite the theory into this sort of quantum circuit formulation that runs in reasonable amounts of time? Now, you'll hear me referencing in this talk a couple of times this idea of resource scaling and resource efficiency and reasonable amounts of time. And the reason why will keep doing that is quantum devices still have to have appropriate scaling. So if you come up with a beautiful formulation of QCD that works great in theory, and then you try and put it onto your quantum device, and you find that your circuit scales exponentially with, let's say, the volume of your theory, you can't simulate that. So you still have to have some sense of efficient resource scaling, even on a quantum device, even in the fault-tolerant era. So now when we're working on NISQ devices, we really have to be careful about thinking about far future scaling arguments. So this is why, for me, this idea of reasonable amounts of time is always part of writing down a theory. Okay, to give you a sense of what I mean by NISQ-era quantum devices, where are we? I want to be simulating on real-world digital quantum computers, so I need to know what's out there. Now, there's been explosive growth in digital devices in the last, I would say, 5 to 10 years. So in terms of qubits, there are now multiple quantum computers with about order 100 network qubits. And in fact, larger systems are coming online in the coming years. So to give you a sense of what I mean by that, so here's IBM's quantum roadmap from 2020. IBM uses superconducting qubits. It's just a type of quantum hardware. And you'll see that by 2023, which was 2 years ago, they said they would have order 1,000 networked devices. Now, they released an updated roadmap in 2023, again, still using superconducting qubits. And the key change that I kind of want to highlight is if you look at 2028 and 2029, so in about 5 years from now, or 4 years from now, they're still not thinking they're going to go beyond 150 qubits or 200 qubits, but instead the number of gates that they can run successfully on their device grows from about 5K, where we're not at 5K right now, we're at about 500. And they say that in about 5 years, they can get to 100 million gates. So you see this growth of what we can carry as we're not going to increase qubits so much, but our gate depth is going to go up. You can also use not superconducting qubits, but trapped ion devices. So IonQ is another device or another company, and you'll see that by 2027 or 2028, they're also saying order 1,000 qubits. Continuum is another trapped ion. The reason why I'm highlighting this is that you'll see that by 2029, they say that they can get their gate count down to about 10 to the minus 10, which means you can run about 10 to the 10 gates before your system decoheres. And so the thing that I'm perhaps trying to highlight in this slide is while it's great that there are existing platforms that have order 100 or order 1,000 qubits, the key thing that the hardware people are really trying to think about is how to decrease their noise so that you can run deeper circuits, right? And the reason why is people talk a lot about fault-tolerant quantum devices. But another issue is that if your device has a decoherence time that is finite, at some point you're going to run out of coherence time. It doesn't matter what you're doing on the software side. If your computer decoheres, you're done. And so part of the issue that we're struggling with as theorists is how do we map our theories into circuits that can actually fit onto these devices given maybe order 500 gates. But this is why this is the NISQ era, is we really can't run a lot of physics at the moment, but we're trying. Okay, so with that lightning fast introduction to classical versus quantum gauge theories, let me move on to Hamiltonian lattice gauge theories, which is what we actually use for quantum devices. I will also say if anyone has questions, I know I'm going quick, feel free to call them out. Okay, so Hamiltonian lattice gauge theory, this is work that goes back to 1975 by Kogut-Susskind. So when we're carrying out quantum simulations, we utilize the Hamiltonian formulation, not the Lagrangian formulation. It's just more innate for quantum computers to use the Hamiltonian formulation. Now for the Hamiltonian formulation, we're going to use continuous time but discrete space. And also we're going to choose Weil gauge, which just guarantees that Schrodinger's equation is gauge invariant, which is nice. Now the nice thing about the Kogut-Susskind Hamiltonian is that you can go from the Wilson-Lagrangian action to Kogut-Susskind, and it's a really nice mapping. Okay, so to write down the Kogut-Susskind Hamiltonian, again, I'm starting off with the abelian version just because it's easy to look at. So Kogut-Susskind, there's two components. On the left, there's an E squared component. That's your electric component. This is built up of electric links, which are, as you might imagine, electric fields living on the links. And then the second contribution is the magnetic contribution, which is traces over plaquettes. The plaquettes are constructed out of gauge links in the typical lattice QCD way. Now, the important thing about thinking about these Hamiltonians and mapping them to quantum devices is that you have to think about the operators that appear in your Hamiltonian and their commutation relations to inform how these Hamiltonians get mapped onto quantum devices, not to quantum qubits. So for the Kogut-Susskind abelian version, the commutation relation is just that the commutator of E and U is equal to U, and that'll inform how we can map this to a quantum circuit. So in particular, when you're thinking about these mappings, choosing a basis for your simulation is of utmost importance. So for example, if I think about the Kogut-Susskind Hamiltonian, those commutation relations, I can choose a electric basis. So for example, in this case, the electric operators are all diagonal with integer values. And then the gauge link operators are simply raising and lowering operators. So what this means, if I think about some state of my Hamiltonian, not necessarily an eigenstate, I just say what the electric field value is on each of the states, and then I can apply the Hamiltonian or the exponential of the Hamiltonian. And in particular, if I think about the action of a plaquette on the state, it just raises and lowers the electric field values on the appropriate link. So the key thing here is that when we think about mapping more complicated theories, this choice of basis will become really, really important. Okay, so we could go from abelian to SUN. This was still done by Kogut-Susskind. In fact, they started off with SUN. So this is very similar to the abelian version, but the electric field and gauge link operators now carry, as you might imagine, color indices. It's a little bit more complicated. The theory now contains both left and right electric operators, because you can have gauge links having gauge transformations act from the left and from the right. But this has all been worked out. You just get slightly more complicated commutation relations. You get two separate SUN algebras. All of this was known. So you might ask, okay, well, this was done in 1975. We understand we didn't have the hardware to simulate it, but why are theorists still thinking about this? What is there left to do? Now, luckily for me, a fair amount. So there's really three fundamental hurdles that have to be addressed before we can really simulate Hamiltonian lattice gauge theories. And these three hurdles are sort of interconnected, so it's really hard to treat one but not the remaining two. But I want to give you a sense of how we go about thinking about them. So the first two hurdles are, the first is that the Hilbert space for a quantum field theory Hamiltonian is infinite dimensional. And as we all know, dealing with infinities and infinite dimensional spaces is hard. So in order to put this onto a digital device, we first have to somehow truncate the Hilbert space, truncate the Hamiltonian. And of course, you need to do this in a way that faithfully captures the desired physics, usually the low energy spectrum. And this is kind of akin to the UV regularization of Lagrangian methods. It's not quite, but it's close. The second is that the gauge groups that I'm interested in, so the gauge groups of the standard model, SU2, SU3, U1, all of those are continuous. But I have a discrete quantum device, and so somehow I'm going to have to do some kind of discrete sampling of this continuous gauge group. Now, what that means is that any sampling method that is chosen has to preserve the gauge structure of the theory. So no gauge violations, making sure it looks like SU3 and let's say not another maybe discrete subgroup. And so in order to address both of these questions, we really have to think carefully about the truncation and digitization of this Hamiltonian. So the general obstruction to this truncation digitization is that the theory has very different properties at large and small bare coupling. So depending on whether you want the theory at strong coupling or at weak coupling, you're going to choose different truncations and digitizations. And unfortunately, the universe has been a little bit cruel to us in this case. And you'll see what I mean in 1 second. So again, I've just replicated the specific SU2 Kogut-Susskind Hamiltonian. And the first basis that we can think of is what's called the strong coupling or the IREP basis. So in this case, the electric component of the Hamiltonian dominates. We can choose the basis of quantum numbers J, ML, and MR, so SU2 angular momentum quantum numbers. Now, this strong coupling basis has a couple really, really nice properties. The first is it's really easy to impose Gauss's law in some sense because Gauss's law acts on the electric links. The states are naturally discretized because J is a discrete quantum number, and there's a natural UV truncation. Just put in a J max. So that's all really good. Now the bad part, which is where the universe has been a touch cruel, is that this really nice strong coupling IREC basis is not really well suited for close to continuum physics. And this is because for lattice theories, the continuum limit is weak coupling. So if you choose a strong coupling basis, you're going to really suffer from truncation errors if you're not careful. So we can say, okay, well, let me go to the weak coupling basis, which is also known as the group element basis or the magnetic basis. And in this case, the magnetic component of the Hamiltonian dominates, so that trace minus of identity minus the plaquettes. And in this case, again, the basis is the group element basis. The gauge links are diagonal. This is well suited for close to continuum physics because the magnetic component dominates, we're at weak coupling. The thing that makes this really hard is that the electric fields are more complicated, and also the gauge link digitization must be done carefully. Namely, how do you sample out of the group element basis so that you ensure that you have faithfully captured the gauge structure? So maybe only one element from every gauge orbit and including every gauge orbit, something like that. And this is why this group element basis is really difficult. Okay, the next thing that is sort of hard is that we have Gauss's law. So Gauss's law for Hamiltonians is not automatically satisfied. And the reason why is that Gauss's law is the constraint associated with the A0 Lagrange multiplier, which we have set to 0 in Weyl gauge. And so what this means is that the naive Hilbert space is now a tensor product of different charge sectors. And one has to carefully figure out how to truncate the Hamiltonian in order to not destroy that. So the key thing, again, is that Weyl gauge is an incomplete gauge fixing procedure. Gauge transformations with only spatial dependencies are still allowed. And now Gauss's law has to be imposed a posteriori. Now, it is a fact that the Hamiltonian does commute with Gauss law operators, and so charge is conserved modulo truncation errors. So what this means is that if you're careful, a state of definite charge will remain in that state of definite charge under time evolution. So there's kind of two approaches one can take to this issue of Gauss law. The first is don't impose any additional gauge fixing, and then just add a penalty term to discourage gauge violating transitions, so charge violating transitions. And this has pros and cons. It can sometimes be easy to implement. You do utilize more qubits. Your gate count might be lower or higher, so there's pros and cons. The second option, which is the option that I prefer, is to do additional gauge fixing. And the reason why I like this method is that if you are successful at fully gauge fixing the Hamiltonian, you now only span one charge sector, and you don't need to worry about your initial state preparation in order to do that. The downside, and this was a big downside, is that you expect an increase in non-locality due to the imposition of Gauss law constraints. And the key thing that I have been looking at for the last couple of years is this question of how bad is that non-locality? Does it give rise to exponential scaling in my gate count, or is it polynomial and therefore feasible? Okay, so the rest of this talk will focus on this second approach. Okay, so I'm going to try and lead us relatively quickly through how we gauge fix a SUN gauge theory in 2+1 and 3+1 dimensions. So again, it's going to be a little bit into the weeds. So the key thing that I want us all to remember is that the reason why I'm advocating for gauge fixing is that it allows us for carrying out good importance sampling when working in the magnetic basis without worrying about breaking gauge invariance. So if you fully gauge fix, you can now impose digitization and truncation without worrying that you're going to do something that causes, for example, charge violating transitions. So that's really the main focus. Okay, so the general idea, if I'm working with a lattice gauge theory, is that there's residual spatial gauge transformations that allow some of the links to be set to the identity. And so we're going to go through the lattice and essentially link by link set them to the identity. Now the key thing is not all gauge links can be set to the identity. The theory is still dynamical. So the key idea is they're going to set as many of the gauge links to the identity, but not all of them. And there's a systematic way to do this, namely max tree. So the max tree procedure says take all of your gauge links in your lattice. I'm only doing a 2D spatial lattice. I can't draw in 3D. The idea is the same. So max tree, you take all of your gauge links and you partition them into two different sectors. The tree links, which are unphysical links that can be set to the identity, and physical links, which are all of the others. Now it's known how to do this for any size of lattice. This is the max tree that I tend to favor. The dashed lines are my tree links, and the purple ones are my physical links. Now this is still an incomplete gauge fixing procedure because all of the gauge transformations start at the origin. So there is still a global gauge transformation, which I promise I will get to before the end. But for now, let's just do max tree. Okay, so with this max tree, now we rewrite the Kogut-Susskind Hamiltonian in terms of tree links and physical links, discard the tree links because they're set to the identity. And then rewrite in terms of new variables in order to preserve the canonical commutation relations. So essentially, we go from Kogut-Susskind, which is written in terms of electric field and gauge and plaquettes. We do max tree gauge fixing. This takes us to these calligraphic E's, which are essentially parallel transported electric links. And then these loop parameters, chi. It's a more complicated looking Hamiltonian. There's an algorithmic way of deriving this, so it's easy to do regardless of the size of your lattice volume. And the key thing is the commutation relations of these new variables are still canonical. They're still the same ones you would expect for SU2, instead of some complicated, garbled commutation relations. Okay, so the key thing that we always try and address is how bad is this non-locality? And I'm going to try and get to that before the end of the talk. So for now, we're just doing max tree. Now I need to parametrize my operator so that I can come up with a basis for simulation, because that'll then inform me about my gate depth and number of circuits that I need. So now, perfect, thank you. So now moving from SUN in 2 plus 1 to SU2 in 2 plus 1 and 3 plus 1. So in particular, there's 3 quantum numbers of the SU2 Hamiltonian. These can be thought of as the total angular momentum and the projected angular momentums in the lab frame and the body frame. So again, we saw that SU2 algebra. And in this case, there's a really nice parametrization using axis angle coordinates. So essentially, any point in a 3-dimensional space, you can think about as an axis and then a rotation around it. Any rotation in a 3-dimensional space can be thought of in terms of that. Now, this is a really convenient parameterization for SU2. Namely, each loop variable is just this SU2 matrix written in axis angle coordinates. And then the electric operators are differential operators, where this sigma and L have definite forms. I'm just not putting them on the screen for you. But with this parametrization, we can now digitize these operators. We can write down a finite dimensional Hamiltonian, which can then be ported into a quantum circuit. Unfortunately, as currently written, we have continuous variables, omega, theta, and phi. Continuous variables generally have to be discretized before you put them on a digital device. So you have to think about how to do that. Now, it turns out that there's a shift of intuition that you can use where the axis angle coordinates are also hyperspherical coordinates of S3. And the angular components of that, so theta and phi, can now be thought of as angular coordinates in S3, described by YLMs, the spherical harmonics. And if you go into the spherical harmonic basis for theta and phi, now they're discrete and there's a natural truncation. Again, just put an L max on it. Now, the variable omega is still continuous, but it's a radial coordinate. And due to previous work with Christian Bauer and myself, we can digitize it using previous methods. Essentially, as you go to weak coupling, the support for omega is finely squeezed around omega equals 0, so you can truncate it nicely. Okay, and perfect. In 3 minutes, I can show you how to finish step 1, which was to gauge fix fully. So the observation that we have is that this SU2 Hamiltonian can actually be thought of as a system of rigid rods of length omega. Again, this hyperspherical picture. So each rod is length omega, and then its angular position is given by theta and phi. The quantum numbers L and M are related to the total color charge of the system. So the total color charge of the system is the difference between the lab frame and the body frame. So the question is this remaining gauge redundancy, this global gauge transformation, somehow related to the rotation between the lab and body frame? So to make it a little bit more clear, here's my lab frame. I have a system of 3 rods. Again, not drawing more rods because it's just more complicated. If I carry out an Euler rotation on that, I can go into the body frame. And what I'm trying to motivate is to change the basis that we're using from this omega, theta, and phi to omega, a couple angular coordinates, and then this alpha, beta, gamma, which is the Euler rotation. Now, this is just a pretty picture. It doesn't mean anything unless you can actually implement it into a Hamiltonian. And luckily for us, this is actually doable. So the general idea is that this appropriate basis change will lead us to a fully gauged fixed theory for arbitrary volumes of SU2 in 2+1 and 3+1. So if I just use the magnetic basis, I go from omega, theta, and phi to these angular coordinates. If I use the mixed basis, so omega, L, and M, to this more complicated one, the key thing to notice is that this alpha, beta, gamma, or lambda, M, and N are the total charge of the system. So now I have in my Hamiltonian, in my basis, a way of defining the total charge. Now, after calculating all possible matrix elements, yes, and arbitrary volumes, which is really cool, we can make three important observations. The first is that no operator can change lambda, which is the global charge, which means it's trivial to construct a Hamiltonian that spans only one total charge sector. And the second is that no operator can change more than 4 discrete quantum numbers at a time. That change can only be changed by -1, 0, and 1, which means that the Hamiltonian is sparse and can be simulated efficiently. So we have successfully fully gauged fixed pure SU2 in 2+1 and 3+1, and it can be simulated efficiently. Now, since I'm running out of time, I'm not going to go into great detail about the cost savings of Kogut-Susskind versus fully gauged fixed. I do just want to quickly highlight that if I do the duplicate universe and I do Kogut-Susskind and I have a J max of 1, the dimensionality of my Hilbert space is 10 to the 8. And we can go through the algebra later. If I do fully gauged fixed and I go to a higher J max of 2 and N max of 2, it's only 75. That's really, really nice. That's actually now completely feasible, both on quantum devices and on classical. And that brings me to my conclusions. So quantum computers have a fundamentally different computational strategy and will provide novel probes of fundamental physics in particle and nuclear, or fundamental questions in particle and nuclear physics. My two main takeaway points are removing all redundancies in gauge theories leads to highly non-local interactions. These aren't always disastrous. Also, don't worry, I've only done SU2, but we are thinking about fermions and SU3. And lastly, what I'm really trying to convey is that exploring the properties of various approaches to lattice gauge theory Hamiltonians is of utmost importance in the NISQ era. Thank you.
Thanks a lot, Dorota. We have plenty of time for questions. See one over here.
So is it possible to also use this for classical methods that work in the Hamiltonian formulation, like tensor network methods or neural quantum states and so on?
Oh, good. So this is a really great question. And I will say, so I am not an expert in tensor networks. So I will say essentially at any place that you need a truncated Hamiltonian, this works. Because everything that I showed had nothing to do, like I didn't show the quantum implementation, right? It's just how do I take a SU2 infinite dimensional Hamiltonian and squeeze it down into a truncated one, and then try and do it as resource efficiently as possible. So yeah, I mean, as long as the dimensionality of your Hilbert space scales appropriately for these methods, I don't see why not. I mean, when I'm doing tests of these Hamiltonians, I throw them on this laptop. Well, not Kogut-Susskind, because I can't do 10 to the 8. But yeah, I would imagine so, and I'd be curious to explore whether that's actually true.
Okay.
This might be a very naive question,
Yeah.
but are there any Gribov ambiguity issues in this gauge fixing? Have you
Oh,
thought about that?
so I don't have a definite answer. My gut feeling on this is that there isn't, though I saw someone very much nodding in the audience, so, which I'm like, my feeling is there isn't, because I don't really see how they would emerge, because this max tree gauge fixing, I mean, there's different conventions, but that's not the same as an ambiguity. And then the sort of final rotations around the origin, there's different conventions, but that's not an ambiguity. However, I don't exactly know how to check for Grabowska copies, so if you have a sense of how to do it, I would love to talk, because this is why I was like, oh, that question. It nags at me, so.
Very interesting talk. Well, maybe I'll comment on this last one, which is not my question, but the Grabowska ambiguity is when you try to do a Lorentz invariant gauge fixing, right? And your tree diagram, of course, completely destroys the symmetry of the system.
Yeah.
So clearly in a discrete system, you can avoid it. But the price you pay, and so this is really my question. First of all, I think it's a great talk, and you should explore all kinds of possibilities. But the price you pay is that your particular gauge has broken the symmetries in space-time, right? I mean, you see lines this way, right? So this means that any errors that you get here will imprint errors on breaking Lorentz invariants. And so I mean, yeah, of course, if there's no errors, it's fine, okay? Yeah. And non-locality becomes a problem. But so anyway, that's a comment. Here's the other branch, which I think you should think about, and you mentioned briefly. When you go to the electric basis, this is called quantum links. It was explored.
Yeah, of course.
Yeah, and then you have gauge invariance exactly imposed. And but the idea that it's only a strong coupling is not clear. There's strong evidence that it may be in the same universality class. So in fact, this is a discrete, just like the Ising model is in the same class as 5-4 theory. So the strong coupling basis may in fact be complete. You know?
Good.
So that's the question, but you know, we should all look at all possibilities.
Yeah, and so I want to touch on a couple, and then I saw Alexi with, so my statement about the strong coupling basis, or the irrep basis is a strong coupling basis, that's not to say that it only works at strong coupling. It's how bad are the truncation errors, right? So if as I go to weaker and weaker coupling, in general, naively speaking, and this is particularly for the irrep basis, the truncation errors can grow as you go to smaller. So of course, if you can include all of the irreps, you would have no issues. It is a complete and orthonormal basis.
It may in fact have no errors, just like the discretization of space-time is in the same universality continuum.
Well, it's truncated.
That is a harder question, and I have
This is known to be true
for quantum link models, which have altered commutation relations, my understanding is, but we can definitely talk about this online.
conjecture, but I'm just trying to keep that alive.
Yeah.
Conjecture disproved. So let's take a question from somebody who hasn't asked one before today.
Hi. It seems like an interesting toy target is just to consider Z2 lattice gauge theory and study hadronization. You know, you have 1,000 qubits, you can have a 30 by 30 lattice, shoot some glue balls at each other, and ask how many glue balls are made. What are the prospects of thinking about that?
Good. So now I have to remember back to literature. So I mean, people have thought about Z2, people have thought about glue balls and hadronization and all of that. So I would imagine that there is work on that already. I'm not quite sure how much has actually been simulated. If anybody knows the reference, feel free to yell it out. I mean, Z2 is nice, right, because there's very small numbers of degrees of freedom on each link. So you can even probably go to reasonable lattice sizes. So yeah, I think is an interesting target, and I imagine that there is some work already done on it, and if not, it should definitely be done. Hopefully that kind of yeah.
So is the square lattice the best kind of lattice for quantum simulations, or should one explore other lattices as well?
You're thinking about like the trimond or things like, you're thinking about the, not the rectilinear, but.
That's right.
Yeah, so this is a great question. So the lovely thing about where we are right now is people are thinking about these questions. You can basically ask any question of, is this the best way? And the answer is, we don't know yet, let's explore. So there is, in fact, work on both the trimond lattice and the honeycomb lattice that is exploring this. So again, the thing I want to highlight is, we're really in the early days of exploration of how we actually can carry out quantum simulations of Hamiltonians. And so a lot of the lore that has been passed down might not hold, right? So for example, my interest in this was, I've always been told if you gauge fix fully, the non-locality will make it completely unfeasible to simulate because of exponential cost. And turns out that's not true. So yeah, long story short, yes, people are thinking about us. We're not sure whether the square or rectangular lattice is the best one.
Yeah, thank you for the great overview. Just suppose you have a very capable quantum computer. What approach would you follow to simulate SU3 QCD with fermions? Is there anything,
Okay.
or at least an approach that you would know to get into that direction?
Yeah, SU3 is a beautiful theory.
We all agree.
Yeah, it is hard. So for example, you can do a version of the IRET basis for SU3. So this is essentially Kogut-Susskind. You can do it in 2+1, you can do it in 3+1. There is nothing inherently wrong with that approach. And in fact, it might, in the long run, that might be the right approach. Now, if you're asking me, can I put this onto a quantum device right now? Ooh, the gate, the noise. I mean, I'm constantly thinking, my grad student tells me, you have 500 gates. What do you want to do with them? And I go, I can't do a single time step with that. And they go, well, okay, that's too bad. You're not putting this onto a quantum device. So, yeah, I mean, I know people have thought about how to do SU3, and I think people maybe have done or are starting to do one plaquette, but like that's really the limit of what we can do in terms of gate count. Because again, it's the thing that's really getting us is not qubits, it's the gate count. So.
There's another question.
Can you expand a little bit on extending the gauge fixing to SU3? Are there new challenges with this, or is it more or less straightforward?
Yeah, sorry. Again, SU3 is really, really hard. So part of the issue, sort of the most blatant complication that I see in the fully gauge fixing is we really use this idea of SU2 related to S3 and Euler angles and this sort of very physically motivated lab to body. That no longer holds in SU3. And I don't have very good intuition about what SU3 actually looks like. So for example, one might say, okay, well, you got a lot of, you made a lot of progress thinking about the axis angle coordinates SU2. Is there an axis angle formulation in SU3? It turns out the answer is yes. It is not nice to work with because in SU2 axis angle, your angles all go from 0 to pi or 0 to 2 pi. It's a fixed range. The one axis angle approach to SU3 that I have seen, if others have seen others, please let me know. The range changes depending on the eigenvalues of your matrix. That's not feasible. So it really has to do also with SU3 being rank 2. And so it's one of those things where the extension is not obvious and we just kind of have to hit our head against the wall and hopefully something happens. I mean, the nice thing is that there are other approaches that don't rely on fully gauge fixing, right? There's this discrete subgroups, there's other continuous variable forms, there's the IREPs. So if we don't figure out the fully gauge fixing for SU3, there's still a lot of really interesting things that can be done. But yeah, I would say rank 2 and cubic is.
I think whether you care about this depends a lot on what your physics goals are, but there's a huge literature in condensed matter theory of realizing gauge theories as low energy physics of spin systems, for example, where the Hilbert space really is just a single qubit on each site, for example. And even gauge theories with continuous gauge group. So those are examples where somebody has figured out an efficient way to fit the Hilbert space of a gauge theory, at least some part of it, into a very small system. So perhaps we can learn something from that.
Yeah, I mean, I'd be very interested to talk, because I have very little overlap with the condensed matter side, and so I know some of this, but I would love to talk more and see whether there's things that we can port over to QCD. Thank you.
In my misspent youth, I looked at some discrete subgroups of SU3 for some reason, and there's delta 3n squared. So, I mean, you could take n large, and you can get, some approximation to the. I don't know whether that would be something useful.
Yeah, very good. So there is work on using discrete subgroups of SU2 and SU3. My understanding, and please correct me if I'm wrong, is that there is a finite number of discrete subgroups. And so one of the things is
there are some infinite sequences
that can do it. Okay, this is where you were getting.
Whether they really cover things well enough, I don't know.
Yeah,
but there are definitely infinite sequences for both.
Okay, so good. So this is good to know, because
like in SU2, you have a dihedral group which covers part of it.
Yeah, so my understanding, so people have thought about discrete subgroups, and my understanding was that the way, at least that they were thinking about it, they had like a max size that they could get to, just because that's where it was not a computational top, but that they said that's the largest group that we can get to, and so then your theory is no longer systematically improvable. And also being able to show that what you've done for that discrete subgroup, can flow to, in the same universality class, all of that. But yeah, I mean, so again, this is the really nice thing, is that all of these ideas either people are looking at or people want to look at, or you could look at, because it really is, there's just so much rich ground to cover at this point.
Well, I think it's time for coffee, so let's thank Dorota again for a great talk, which stimulated so much discussion.